for today's seminar, which is good. Got it. Good. I think now I remembered everything. I forgot. Yeah, right. So we'll do a recap. I'll talk about Bayesian statistical models. We'll have a little bit of break. Then we'll come back. We'll get to today's actual advertised topic, which is implementations of modeling for language change. And I'll take two topics, models of the spread of innovations and a Bayesian admixture model of language contact. And then that leaves one more advertised topic for this week that I'm going to bump into next week, and that is phylogenetic models. Something for recap of last time. So the first section last week was titled Models Throughout the Sciences, and this was a bit of a high-level sort of meta tour of some concepts around the use of models in the sciences. We first saw that models typically provide a representation of a target system, and often that representation is quite idealized. Moreover, we noted that idealization in models is not a failure to be realistic. In linguistics, we often are very, very concerned about all of the details, and rightly so. We turn to models, we notice a lot of the details are not there. Well, it's not a failure to be realistic, but it's a choice to be simple. And it's a strategic choice because it opens some doors. And that is captured quite nicely in this quote that I had last time, that idealizations are a crucial means for science to cope with systems that are difficult to study in their full complexity. We saw that we can learn from models as we build them initially, as we manipulate them or run them if they're computer models, and we can learn from them as we then try and relate them back to the target system that they were supposed to be representing in the first place. And the learning that can happen can be about the models themselves, it can be about the theories that perhaps inspired the models, and it can be about the phenomena that we're attempting to model in the target system. And we saw that there's even this case, which is a little bit counterintuitive perhaps at first, that even false models can have a role to play in scientific progress. Then our second topic was a very quick look at models of language change. So there I mentioned 4 areas of modeling language change. I talked about modeling cognitive models that look at modeling minds and processes of inference, which we mentioned, the importance to go across generations. Spread models that look at the movement of properties of languages through populations or geography. Models of grammar change, that is perhaps a model of knowledgeization or grammaticalization. And models of dissent and relatedness, so subgrouping and proto-languages, stuff like that. And then we had a nice discussion that followed where various people pointed out that these are not mutually exclusive things that you might study, and indeed how much they do overlap will depend on how you go about them. So the more idealized they are, perhaps the less overlap they have, but as you get less idealized, everything starts mixing in together, because after all, they're all ways that each picks out a few pieces of the big overall picture, and the more we get more of the overall picture, the more they might overlap. At that point, we took a break, so we were pretty busy last week, and we looked at probabilistic models, and where my really only one point was how to think about randomness in terms of models. We talked about randomness, and we break uncertainty when the outcomes of a process are intrinsically, irreducibly uncertain, and randomness as epistemic uncertainty, where the outcome is uncertain due to some lack of information. And we took the example there of tossing a coin, where if we knew all of the physics, we probably could tell you whether it's going to land as heads or tails, but we don't have all of that information. Because of that lack of information, flipping a coin is, to us, laden with a whole lot of epistemic uncertainty. So that's a kind of randomness. And then I went through the argument that for why in an idealized model, we might end up modeling a process in probabilistic terms if model internally, the process is subject to epistemic uncertainty. That is, the model doesn't know all of the details it needs in order to fully predict what's going on. Even though outside of it, we scientists do know all of those additional details and can say, well, this is deterministic. If you just pay attention to this, you would know the answer. But the model being idealized, can't pay attention to that. Something we find that in models that get developed. Finally, we considered quantitative and computational models, also known as formal models, including a few notions that are worth knowing about. We noted that they can be expressed as equations or algorithms. We noticed the growing recognition that in order to secure scientific advancement, even in the social sciences, sometimes we need formal models. Most of all, formal models make it much easier to see where we're currently wrong and put down arguments for why someone's proposal is not quite right yet, and then we can do something about it. So it's not about scoring points, it's about knowing where we can improve. If we don't know where we can improve, we kind of wander around for a long time, where we'd like to all be making progress. I mentioned Geston Martin's proposal of a specification, which is a description of an algorithm and what an algorithm will do, rather than the algorithm itself, and it's a sort of preliminary to writing the algorithm, and it gives greater structure to the process of learning about models, and also talked about probability distributions as a key idea for formalizing uncertainty. So what's the probability that we believe this is going to happen, the probability that's going to happen, and this is going to happen? That's a probability distribution. And those things can be very important when you're running probabilistic models. What we didn't have time for last week, and what we can now move on to without further delay, is Bayesian statistical models. Almost no delay. All right, so almost certainly you've heard the phrase Bayesian statistics. For people who live and breathe this stuff, just bear with us. And like I say, come to me afterwards and correct me if there's something that I'm not quite right on. But for those of us who don't live and breathe Bayesian statistics, we probably still heard the term. You probably still read it somewhere in a paper that you were interested in. Also called Bayesian model, Bayesian reasoning. And like I say, probably you've read papers where authors use this stuff. Or you use it yourself, you do. Now, there are many ways that you can characterize Bayesian statistics, but for linguists, I would like to put it this way, that Bayesian statistics is a branch of probability theory that's concerned about conditional probabilities. It's particularly concerned with conditional probability, that is, probabilities of the kind, what is the chance of A given that B has happened or is in the environment or whatever. That's one important thing about them, and the other one is that they provide a particularly elegant and clear method for the integration of top-down and bottom-up information. And that's really the magic of them. It's this integration. I'll talk about conditional probability, then I'll talk about Bayes' rule. You will see some equations here, but I'll walk through them all. I'll come back to the issue that we discussed last week about computational challenges related to complex calculations and how even if you have the biggest computer in the world, sometimes there's a problem that's too big for that computer. So what you do. And then I'll talk about some ways that Bayesian reasoning has relevance to models of language change and models of cognition. Right. So let's first lay the groundwork for Bayesian statistics, and that is conditional probability. Suppose we're interested in the probability on any given day that I am carrying a water bottle with me. It doesn't happen every day, so we can't just say you'll definitely be carrying it. We might say that the probability is 60%, 0.6. On any given day, there's a 60% chance that Eric will be carrying a water bottle. However, we might also notice that the probability differs according to the temperature of that day. So for instance, the probability that I'm carrying a water bottle if the temperature is above 30 degrees is not 0.6, it's 0.9, it's 90%. So this is a conditional probability. It's the probability of one event, being carrying the water, given another one, the temperature. And we could write, we write conditional probabilities in this format with probability of A and then the bar and then B. That's the probability of A given B. And so if we're looking at the conditional probability of me carrying the water bottle, given the temperature on the day, we might draw up a little table, say something like this, where we have the temperature in one column. And then over here, we have the conditional probability of me carrying a bottle, given that temperature. And so this is basically conditional probability. And we'll now look at how Bayes statistics deals with conditional probabilities. So conditional probabilities are particularly useful in two cases that are very important for science. They're very useful for expressions of predictions. So that is, given the existence of a certain causal event, so given a cause, what is the probability that we'll also encounter a certain kind of evidence for it? So for instance, if you know the temperature, hang on, this is how I want it. Got to get it the right way around. So we're looking at me and my water bottle. We know the temperature. This is the thing that tends to cause me to take my water bottle with me or not. So we know the causal event. If you know the temperature, then because of that, you can actually, with some reason to it, modify your prediction about whether I'll carry a water bottle. Now, you can't know for sure here. Remember, we're using probability theory, which is all about quantified uncertainty, because there's a degree of uncertainty here. So you can't know for sure whether I'll be carrying my water bottle, but you can quantify and modulate your prediction of how likely it is that I'm carrying it in this way. So conditional probabilities are very useful for predictions, which are obviously something that we do a lot of in science. Secondly, conditional probabilities help us make inferences. That is, quantifying the probability of there having been a causal event, given that we find certain evidence for it. And to illustrate this, suppose that you are talking to me on Zoom. You don't know the temperature in the city where I am, but you observe that I have my water bottle with me. So now you can infer how likely it is to be hot or cold in the city where I am. So specifically, you would infer that it's more likely to be hot where I am than to be cold. Now, again, you can't know for sure because we're dealing with uncertainty here, but you can quantify your uncertainty and adjust your estimate of the probability of the various temperatures in accordance with the evidence that you've got from seeing me with my water bottle. And we'll see in just a minute how you can do that rather exactly. For now, though, we can note that inference is going to be particularly important for studies of language change, where very often what we're interested in is inferring causal events in the past, which we can't see directly, given the evidence that we obtain for them from observations in the present. So, given that, how do we actually quantify these inferences? And that brings us to Bayes' rule. That thing will return in about 20 minutes. That's my prediction. Right, so we're under Bayes' rule now. So I'm going to talk about Bayes' rule, but let's first see where it comes from. Let's derive it, because it's not actually terribly mysterious, although it sounds like magic when people put it in their fancy papers. So you might recall from some point in life, probably you did this in high school, that you learned that the probability of A and B is equal to the probability of A given B multiplied by the probability of B. And if you have since forgotten that, that's fine. I've just reminded you. Now, alternatively, it's also equal to the probability of B given A multiplied by the probability of A, which of course we remembered that one. But in any case, that gives us this little equality here. Now, if I'm going to divide both sides by the probability of B.
There's somebody who wants to answer.
Yeah. Oh, and now it's taken me now. Right. Okay, so we had this equality. I'm dividing both sides by the probability of B, and so we get this. Bear with me, just a little bit of maths. Now, let's start giving some sense to this A and B. Let's say that the event B here is the event of obtaining some evidence about something. So let me just update our formula. All I've done here is where I used to have a B, I now have E for evidence. So B now is an event of obtaining certain evidence. And let's say that A is a causal event, which may have led to this evidence. So again, we'll update it here. And I'm not going to write C for cause. I'm going to be a little bit more explicit. It's the hypothesis that we have of a certain causal event having led to those that evidence. And so I've just rewritten again where I used to have A, I've now put H. And so we'll have that now with hypotheses and evidence. And this is Bayes' rule. This is or Bayes' theorem, and it's a formula for working out inference. What is the probability of a certain hypothesis being true given some evidence that we have? So for example, what is the probability that today's temperature in the city where I am is over 30 degrees, given the fact that you have the evidence that I have my water bottle with me? And so that's the kind of thing that we could do using Bayes' rule. All right, fine. Why is that such a big deal? And why do people sound so smart when they say Bayes, if that's all it is? Well, to answer that, we need to understand a little bit about just how magical some of the parts of this equation are. So here's Bayes' rule again. First, we've noted that this is a formula for making inferences. Moreover, it's a probabilistic formula. Recall that probability theory, of course, is our formalization of uncertainty, and therefore, Bayes' rule is a means for making quantified inferences under conditions of uncertainty. That's pretty cool if you're a scientist. That's what science is largely about. It's making inferences about causal hypotheses in an uncertain world, based on evidence that we get. So that's part of why it's important, not because it's particularly complex, but it really matters to things that matter to us. But there's even more than this. Let's look at the pieces of the equation. So this piece here is something we've seen before. It's, if you look at it, it's a prediction. So it's the predicted probability of obtaining our evidence if the hypothesis is true. So if the hypothesis is true, what's the probability we'll get the evidence? That's a prediction going from the hypothesis to the evidence. And this particular piece of the formula is going to change depending on what our evidence is. So it's sensitive to the evidence that we've obtained. Moving on to the second piece over here, I hope you can see the color. This is going to get really exciting in the second half of the hour, and I've got a lot of color. Anyway, moving on to the next piece here. This piece, interestingly, is totally independent of the evidence. The evidence is not in that part of the formula. This piece yeah, sorry, that's all I wanted to say about that. It doesn't have anything about the evidence there. And then the part on the bottom, I'm going to set aside for about 10 minutes and we'll come back to it. It's a little bit tricky, but we'll just leave that there. But here's the real power. This part here is effectively about bottom-up information. This is about the evidence that you have. This part here is top-down. This is what you think is the likelihood, the probability of your hypotheses independent of the evidence. And that's really quite nice that we're splitting it up. So what Bayes' rule is doing in a really quite elegant way is allowing us to integrate bottom up and top down information. And I'll make this much more concrete in a couple of slides. But I just want to say at this point that it's part of its power is that it just so elegantly splits these things up and allows us to put them together. Okay, now let me move on to my example. I do. Okay, coffee, tea, and cake. So let's work through an example to see how all of this functions, just to show you that it's really not that complicated. It can be done with pencil and paper if you take a nice simple example like this. So here is Reverend Tom Bays. Every afternoon at exactly 3 o'clock, he takes a break from work. Clear his mind, he has a drink of either coffee or tea, and sometimes he eats cake. So to quantify matters, 20% of the time he drinks coffee and 80% of the time he drinks tea. And the probability of him eating cake depends on what he drinks. So if he drinks coffee, he has cake 40% of the time. If he drinks tea, he's less likely to have cake. It doesn't go together, it's fine as well. So if he drinks tea, it's 20% of it. Today, you saw Tom at 3 p.m. and cup in front of him, you saw that he was drinking something and he was eating cake, but you didn't know what was in the cup. So what's the probability that he drank coffee? That is, please infer the probability of the coffee hypothesis given the evidence that you have that he was eating cake. So before we do this using Bayes' theorem, let's try and just do it intuitively. And we'll try and do it intuitively in two ways. First, let's go on bottom-up information, bottom-up principles. We saw that he was eating cake. That's our evidence. That's our bottom-up information. So notice that the probability of Tom eating cake is twice as high when he's drinking coffee. So the bottom-up reasoning suggests he was drinking coffee, right? Because he was eating cake. Now let's try from top-down principles. Based on what we know generally, irrespective of any particular observations, we see that, well, the Reverend Tom drinks coffee only occasionally. He drinks tea 4 times as often as he drinks coffee. So the top-down reasoning says, well, surely he was drinking tea. Right, so we've got competing bottom-up and top-down information. Well, let's integrate it. And we can integrate it using Bayes' rule. So here's the probability of the evidence given the hypothesis. That is the probability of cake being eaten given coffee, which is that, 0.4. And here's the top-down probability of him drinking coffee, which is 20% or 0.2. So at this point, we've already worked out most of the equation. At the top, it's going to be 0.4 times 0.2, and we've just got to work out that thing on the bottom. So let's now talk about the denominator of the equation. So to deal with the denominator in Bayes' rule, first, we're going to need to take a little step backwards and understand a little bit more about our hypothesis. So here's the formula. And recall, we're attempting to infer the probability of the hypothesis H. That's just one hypothesis given our evidence. Now that hypothesis H is one option in some larger set of conceivable hypotheses. And we call that set of conceivable hypotheses the hypothesis space. And in our current inference problem involving Tom and his cake and what he's drinking, the hypothesis set is nice and small. The hypothesis space is nice and small. It's just a set containing 2 possible events, that he was drinking coffee or he was drinking tea. More generally, though, the hypothesis space would have any number of hypotheses in it, and we'll call that number n, and n could be very large and, in fact, even infinite. But don't get scared here. We'll work it out. Right, so with that knowledge of the hypothesis space in mind, so we now understand a little bit about hypothesis spaces, let's return to the question of what the denominator is. What does it mean, the probability of the evidence? So here's what it means. And just bear with me, this is going to start ugly and become beautiful. So it's just this. It's a string of products, and it looks rather daunting, but actually you need to break it down into a bunch of bits. It's made up of all of these bits, each of which has exactly the same form as the top part of the equation, except now the first one refers specifically to hypothesis 1 in the hypothesis space, specific to hypothesis 2 in the hypothesis space, and all the way up to the nth one in the hypothesis space, and we just sum them all up. And that's it. For those of you who are mathematically minded, that means that this is a normalization factor here. Coming back to our case of Reverend Tom, it means that the denominator is simply this. It looks a bit long, but again, you can break it down into these fairly simple bits that resemble the top part of the equation. So the denominator there is the probability of cake given coffee times the probability of coffee plus the probability of cake given tea times the probability of tea, which means we're now ready to solve our solution and integrate our top-down and bottom-up information. So back to our formula. To finalize our calculations, we need to assign a value to the denominator. On the last slide, we found out that it was this, and we can then fill in all of these probabilities because we have them all. They're there. And so if we put in the numbers, we get that and works out to 0.24. So if we take where we were up to before, plug in the last number that we need down here, we get our answer. So we derive the Bayesian estimate of the probability that Reverend Tom was drinking coffee given that he ate cake, and the answer is 1/3. That is what you say is the probability that he was drinking coffee, integrating your top-down and bottom-up information. And you'll notice it's different to the top-down information. It's different to the bottom-up. It draws them closer together and they kind of meet in the middle. That's the result that you get. Now, what's important here is that we did all of this by this process of integrating bottom-up with top-down information. And in doing so, we're performing precise, quantified inference under conditions of uncertainty. Because remember, all we saw that he was eating cake. In addition to that, we use some probabilities. None of these say he will eat cake or he will drink coffee. They're all probabilities. All of this is uncertainty, except for that evidence that we got, but we could put it all together in a quantified way, which is really nice. So what is so important then about integrating bottom up and top-down information? Oh, I didn't want to get to that yet. Perhaps the most single important point is that very many tasks of inference are simply unsolvable with any kind of accuracy unless we use both bottom-up and top-down expectations. So you can't just go out there and use your observations in a lot of cases. You need to bring to it some top-down expectations as well. There's very good reason to believe that when we humans are just walking around in everyday life, constantly doing inference about what's going on, that we do this all the time. So here's a nice one. Consider this just everyday problem of inference. A woman is walking down the street when suddenly she pauses, turns, and begins running in the opposite direction. Why? Okay, there's your bottom-up evidence. As a human, I bet you can come up with some scenarios that do a lot better than just going, I don't know, she's crazy. So like, just what's one thing that comes to anyone's mind? She forgot something. Yeah, another possibility. If I push you further, like what if I said, oh no, I'm gonna give you some more evidence. She didn't forget anything, yeah?
She was scared.
She was scared of something? Yeah, good. To come to those inferences, you're applying a lot of top-down information. You're applying top-down information about the fact that, well, sometimes people forget things. Sometimes people get scared. That's much more common than someone being a complete nutter who just changes direction in the middle of walking somewhere. And that's why we wouldn't normally, if we see a person on the street doing that, think that this person is crazy. We would think that, oh yeah, maybe forgotten something, maybe scared. So this is integrating a lot of very important top-down information together with the tiny scraps of bottom-up evidence that we get. Or here's a linguistic case. What's the most probable family tree for languages A, B, C, and D, using a mix of bottom-up and top-down information? The bottom-up information is evidence that we've collected from their basic vocabulary, but then the top-down is an expectation that if we see form meaning pairings in words, this is more likely due to cognacy than chance. And why might we have that top-down information? Because these languages are all next to each other somewhere rather than 4 different continents, something like that. So we also use a combination of bottom-up and top-down when we're doing linguistic problem solving as well. So integrating those two kinds of information is really, really important very, very often. And that is why you see the word bays everywhere you look. It's because it's a way of doing that task well. So before I move any further, I just want to get a little bit of technical terminology out of the way. This is not because you need to memorize it, there is no test, but you'll see these words floating around. So this part of the formula up here is called the likelihood. This is the one which I said was a prediction. What would you predict? How probable would you predict the evidence is given the hypothesis? This is called the prior probability of the hypothesis, or just the prior, and you've probably heard that term floating around. This one over here is called the posterior. Sometimes you'll read that and it might sound really mysterious. It's just the answer that you got, essentially. And this one is rarely referred to, but you could call it the marginal. Like I say, you don't need to memorize these. I mention them because you will see them in the literature. Particularly, you'll see people talking about prior or priors. Why? Because these are our top-down expectations. So when people say, what are the priors here? What is the top-down information that you're bringing to meet the bottom-up stuff that you're getting from the evidence? Okay, great. So we've got it. We've got the equation that unlocks the universe. So why are we still like sitting here not unlocking the universe? Let me add a dose of reality. So mathematically, Bayesian inference is the ideal way to integrate bottom-up and top-down probabilistic information. It will give you the best set of answers. However, it's also quite impractical or even impossible to calculate. How annoying. So this is going to have some obviously really important ramifications. Firstly, for scientists who are wanting to use it, that's going to put limits on us. But also, what about this? It's going to put some limitations on human brains that are trying to use it in order to work out why that woman suddenly stopped and turned around and ran the other direction. So what should we do if Bayesian inference is ideal, but out of reach often? So in both cases, whether it's for scientists or for human brains, this fact basically defines a new problem, a new target that we want to aim for, namely good approximations to Bayesian inference. If we can't do Bayesian inference itself, can we get something that's really close to it, but we can actually compute it? So let me first talk about why Bayesian inference would be unattainable in this way that I'm talking about, and then I'll talk about some approximation. So first, why Bayes can be unattainable. So here's Bayes' rule. And recall here that the H is just one hypothesis in a larger hypothesis space. And moreover, there we are. The marginal here is spelled out like that. Now, I'll mention two reasons why this can get problematic. The first reason is that for many problems, the hypothesis space can be utterly enormous. So consider the hypothesis space consisting of the set of all possible reasons for someone's actions. It's pretty big. In fact, it's not even clear like where the boundaries would be. So that's a big hypothesis space. or the set of all possible family trees for 50 languages. How many different ways can you draw a tree that connects up 50 languages? You may be wondering. Oh, it's 510 septillion possible trees. That's a pretty big hypothesis space. So if you want the exact probability for any of these hypotheses, given your evidence, you'd have to complete, oh boy, this equation here, plugging in all of the numbers for 510 septillion hypotheses, which is just not going to be feasible. Now, here's the first nice thing. If you don't care about the exact probability, but instead you're only interested in knowing which hypothesis has the highest probability, then for technical reasons, you don't actually have to calculate that. You can just ignore this bit. Just set it to K for a constant, because it doesn't respond to the hypothesis. We're just asking which hypothesis has the highest probability. We don't have to calculate that. That's great. However, you would still need to go to every single hypothesis in the hypothesis space and calculate the rest of the equation, which is also going to be infeasible. So this is the first reason why calculating Bayes' rule exactly can be infeasible. The second reason is that the likelihood can also become extremely difficult to calculate, even just for one hypothesis. So remember that the likelihood is essentially a prediction. It's the probability that you would predict that you get the evidence if the hypothesis were true. That can be sometimes hard. For example, what is the probability of observing the Earth's current climate, giving a specific hypothesis about how the ocean absorbs CO2? 0.2, 0.1. This is not a table that I can go and look up like the Reverend drinking coffee and tea. That's a really hard prediction to make. So we have two big challenges here. We have searching through enormous hypothesis spaces and calculating difficult hypothetical predictions. Many mathematical and statistical PhDs have been written on how to handle these problems. So the first problem began to get solutions in the 1990s with methods like Bayesian Markov chain Monte Carlo methods. You may have read that in a paper and gone, what's that? That is about searching large hypothesis spaces. That's what it is. It gets called MCMC. The second problem is still very much at the cutting edge. Since kind of the mid-2010s, mathematicians started developing a lot of what are called likelihood-free methods, because remember the problem is the likelihood up here, such as approximate Bayesian computation, which gets the cute name ABC because it's not easy. Most commonly, these involve not actually calculating the likelihood, but instead running a large number of simulations, like climate simulations, in order to estimate the likelihood. So we run lots and lots of simulations and see what the answer is and kind of average over them. And I should emphasize that it's a lot more tricky than just the simulations. There's a lot more additional maths that goes in, but it does connect back in an important way to something that I said last week about the increasing role of simulations in modeling of things. And you could imagine, for example, simulating scenarios of linguistic change to do something like this. All right, this is all good news if you're a scientist trying to use Bayes' rule. But what if you're a human brain? You're probably not using MCMC or approximate Bayesian computation. Well, who knows? What is the brain doing? But how do we humans deal with probabilities that are impossible to calculate? And this is kind of nice. There's a key notion under active research within computational psychology that a lot of our solution is to use heuristics or shortcuts, which are a good approximation at Bayesian inference, but come at a lower computational cost. So we know that the brain is wonderful, but it's not that big, and so it can't calculate truly enormous things. But if you give it little shortcuts, perhaps it can get there with pretty good answers. Now, of course, there's no such thing as a free lunch. So these heuristics give you a shortcut, but they come with a downside. Namely, sometimes they fail, and they can fail spectacularly. They're set up to work 95% of the time. I guarantee you, I'll give an answer that's really close to Bayes, but in the other 5% of the time, you're on your own. And that seems to actually be what happens. So a fascinating hypothesis is that many of the classic cognitive biases, the causes where we reason poorly as humans, may in fact be cases where our heuristics, which normally work so well, these are the cases where they fail. And so in the final seminar in week 4, or what would be week 4, we'll see a model of morphological change, which integrates in a small way this kind of notion that we're using heuristics in order to get the answer quickly. And if you find these kinds of things interestingly, here are a couple of quite accessible papers to get started with. I'll pause there because I know some of you will be jotting that down. By the way, we should probably work out a way to share slides at some point. So if you miss something, it's not your last chance, okay? And of course, it is being recorded. So to summarize what we've just seen, Bayesian statistics is a branch of probability theory that's concerned particularly with conditional probabilities, that is, what is the chance of A given B, and which provides a powerful method for integrating top-down and bottom-up information. And that's my presentation of it for linguists. I'm a linguist, most of you are linguists. There are more technical things that you can find. If you go to YouTube and you search for Bayes theory, there's 3 Blue, 1 Brown is a YouTube channel which has absolutely fantastic videos on maths, and he has a really nice one on Bayes theorem. So watch that and then get addicted to all of the other things. Particularly if you're a linguist who finds that you keep on doing more and more maths every year, but it's every year it's longer and longer since you actually got taught that stuff. He has really, really good videos on all sorts of topics, which is really nice. All right, sorry, we've covered integration of bottom-up and top-down information. We covered conditional probability, Bayes rule. We looked at computational challenges that can often make Bayesian inference infeasible. And then I mentioned some of the cutting-edge responses to that, and also touched on ways in which all of this has relevance to the modeling of language change and cognition. And we'll see more of this as we progress through the second hour today and the subsequent talks. So next time someone tries to make you feel inferior by saying, I know that. Top down, bottom up. Got it. Right? That's the main thing. So good. I spoke quickly, so I'm not yet running behind. We're going to take a break soon, but if anyone wants to raise questions or discussion points, we could do that now. Not kind of race through that. Yeah. And why am I Yeah, sorry, yeah.
Yeah, because I'm wondering about the. So in this case, we would have a given idea about what the family tree was like,
Mhm.
and then new evidence comes along.
Yep.
And possibly evidence for which there is low probability given our best
Mhm.
current hypothesis.
Yeah.
This means we have to update.
Exactly, yeah.
Okay, and then how exactly is how exactly was our previous hypothesis top down?
So this one here, I'm saying that over,
Because this seems like a more general principle that
Right.
guides
yeah,
right
so
the
what,
appearance of the evidence.
exactly, so here also things kind of blur. What today is a top-down hypothesis, in 100 years' time, maybe established science is the only way to do things, right? So, what we know from 200 years of work is that this is probably not a hypothesis, this is probably the way the world is, right? However, when we're modeling language change, we might want to treat it as a hypothesis. And in fact, some approaches to inferring trees from lexical evidence actually do treat it as a hypothesis and then also look at the strength of it and so forth. So even though we have very good reason to believe that it's the case, what about when we don't know what the cognacy is, or where there is parallel innovation due to parallel borrowing and stuff like that? It still may make it worthwhile to treat that as a hypothesis rather than a fact. So again, that in a sense relates to this idea of what happens when the model has a very small view of the world. We know that borrowing is going to have certain effects, but this model says, no, it's all trees. How do we cope with that? Well, we just set some things up probabilistically instead of deterministically, which we would do if we had the wider view. Yeah, again, so it can, what's a hypothesis and what's just the model level, or what's just the way the world is, can shift over time. And at that point, I sort of make way for the philosophers of science. But yeah, great questions. Is there another quick one? Yeah.
Do you think you could say a little bit more about how this ties to the cognitive biases that you mentioned? Because they didn't completely catch the one. Is it about?
Yeah, right.
Is it about like hypothesis, or is it about hypothesis?
So I'm glad you asked me if I could say a little bit more about it, because I'm not a huge expert in it. But the idea is, for example, you've experienced a lot of the world. And if you had an extremely powerful brain, every time that you walk out the door and see something, you would take all of that prior experience into account, this huge top-down thing you introduced to it. But your brain just can't go and search through every memory that you ever did. So one of the things that it does is it goes and picks out really salient memories and applies them. Okay. There's some mathematical work that shows that's actually quite well founded mathematically. So if you told someone, you're going to do Bayesian inference, but I'm only giving you a computer from 1985 to do it on, what are you going to do about it? What you would do is say, all right, I'm only going to take the most salient top-down information, I'm going to dump the rest, and I'm going to calculate it that way. And that actually gives you a pretty good answer most of the time. But as you would imagine, maybe you have failed to take into account this less salient but extremely important thing, which would have helped you make a better prediction at the time. It seems that humans do that. We also latch on to really salient things. And here I'm going beyond my expertise. Apparently so, when you get people to do stuff in the lab like this, you can show that the way they act can actually be modeled exceedingly well with these kind of approximations. But again, those papers that I mentioned will have been written by people who are more expert on the topic and will give links to more stuff.
Yes, I don't know if it's related, but no, I just don't understand the notion of probability of the hypothesis independently from the evidence. How can you know that a hypothesis is likely or not?
Right.
Not looking at the evidence.
Yeah. So this is from all other sources. So this could be experience previously, right? So remember, with the Reverend drinking coffee, I said 20% of the time he drinks coffee and 80% of the time he drinks tea. That's just a number that I've tallied up over many years of experience, not paying attention to the cake. Right.
It's not independent from the evidence.
Well, it's ignoring the evidence, right?
Yes, knowing the evidence.
Right. So, well, what's independent of what? So in that little world that I was creating, what he drinks is causing probabilistically what he eats, right? So it's not the case that the cake is causing what he drinks. So what's independent of what, right? This is part of it too, right? So that you're now anyone jump in. Again, this is getting beyond what I'm expert in. But the idea here is you've got a hypothesis of something that's causing the evidence. Right. Yeah. So when you do causal inference, right, which is you can do with Bayes theory, then things they aren't independent of one another, but the way that they're independent or not is captured in the expression there. Yeah. Okay. All right. I better take a break there for let's take 5 minutes break so that I get everything packed into the second round. All right. So let's go with the second half of today's seminar, where we finally get to implementations of modeling for language change. So in the first hour, we looked at Bayesian statistical modelings, a topic that I had carried over from last week, and you can see why I did. If we tried to do that in 20 minutes, it would be a bit painful. Now we move on to the advertised topics for today's seminar, implementations of modelling for language change. And I have two parts here. First is models of innovation spread, and then a Bayesian admixture model of language contact. The advertised topic of phylogenetic models, I'll carry over to next week. All right, so models of innovation spread is our first topic for this hour. Okay, so in historical linguistics, models of spread of innovations can draw inspiration from two main sources beyond linguistics itself. The first is epidemiology, which of course looks at and is very concerned with the modeling of the spread of disease, and the relatively young field of cultural evolution, which is a mathematical field that builds models of the spread of cultural traits. So in this section, I'm going to describe 4 foundational models from these fields, and I'll mention very briefly some studies in historical linguistics that are related to the concepts that I'm introducing here, though the linguistic ones are more elaborate than the stuff that I'll fly through here. So I'm going to look at, is it dropped again?
So again, check the mic, and the mic should be okay, but oh no,
Everything's okay? All right. Right, so I'm going to look at 4 foundational models here. Unbiased transmission, unbiased transmission with mutation, transmission with content bias, also social contagion. Those will turn out to be exactly the same model, though from two different disciplines. And then transmission in social networks really quickly. So our first model is unbiased transmission. So this is a model of intergenerational transmission and the propagation of cultural or linguistic variants, where propagation can entail either the growth or the maintenance or the decline over time in the prevalence of these variants. The model here is highly idealized, and it goes like this. Each generation contains n individuals who possess either variant A or variant B. In the first generation, we just assign these at random. So we set up our generation number 1. At each new generation, same number of new individuals are born, and each of them is going to learn from one member of the previous generation. And that person is termed the demonstrator. So the demonstrator is chosen at random, and then the new generation acquires the variant from their demonstrator. There we go. We have a new generation. And then now the adults, a new generation is born, and we repeat. Each generation just goes on like this, and we can observe what happens to the prevalence of variant A and variant B. So what does happen? Here's a plot showing a population of 1,000 individuals across 100 generations, where we start with variant A and variant B in a 50-50 split. There's 5 lines there. Each line shows one simulation across 100 generations and is showing you the proportion of the A variant from 0 up to 1. So that's with 10,000 individuals. Here's 5 runs when our population is only 1,000 individuals. And here's what happens if you have 100 individuals. And so you might notice some stuff already, right? So the smaller the population, the more variable things are. When we've got a really big population, basically that just stays at 50% and just stays there for a very long time. With a smaller population, we get more variation. And with a really small population, we actually saw that in 2 of the 5 simulations, the prevalence of variant A went to 0. At some point, the whole population was using B. And statistically, that can always happen, even with 10,000 individuals. If we let it run long enough, some population would get wild enough to either eliminate A or B, but it's much more common if we've got smaller populations. So this gives us the first couple of insights into, spread of variants and what can happen over time. Here's the same sizes of populations, and this time, though, I'm starting out in the initial conditions with 80% of the population having variant A. As you see, there's nothing magical about 50%. What's happening here is it just stays at whatever level it started at in a big population. But of course, with small populations, you get this variation. And not surprisingly, with a very small population, what happened was in all 5 of those simulations, it ended up with the whole population having variant A. So this is super simple model. It's not particularly exciting. It's obviously not all that happens in language change. But to return to a theme from last week, it is useful. We can think of this unbiased transmission as a baseline model against which we can compare other models, which are actually more interesting, have more working parts, are more like reality. So let's do that. A second model is unbiased transmission with mutation. This model is the same as the previous one, except that now there's a small chance that a demonstrator has variant A, but the learner from that demonstrator acquires B instead. Or that a demonstrator has variant B, and there's a small chance that the learner will acquire variant A. So this is the mutation part. So we're going to model this. We'll put 2 values in. This is the probability that you've had a demonstrator with A, but you've learned B. and vice versa there. In a population with 10,000 individuals, this is what happens. So this is, here I'm starting a simulation with a 50% prevalence for A, and you'll notice that it goes up in this interesting bend and stops at 75%. What if I set the population to start not with 50% prevalence of A, but with just 10% prevalence of A? What you notice is it also bends upwards and happily ends up sitting around about 75%. Okay, what if I start with 90% A at the start? Well, it just bends down to 75%. And if you want to know why it's 75%, the answer is take this and divide it by the sum of those. The interesting point here is that now we've got something other than just a straight line or just randomness. And one of the things is, have a look at the shape of the curve. In linguistics, we talk all the time about S-shaped curves. That is not an S. That's an R-shaped curve. So again, highly idealized model, but we've got this nice additional thing that we found about it, and we can add this to our sort of set of baselines against which we can compare other models. It would look like this is not yet the perfect model to go off and explain sociolinguistics. All right, now let's go on to model number 3. This is a model of transmission with what's called content bias. In this model, the transmission across generations now gets more complicated. It's going to have 2 steps. First of all, each member of the older generation is going to transmit their variant to one member of the new generation. Just to keep my diagram simple, let's say that they transmit it to the person with the same number on their vest. Right, so we've got this, they transmit it there, which will give these variants to the younger generation. Step 2, though, each member of the younger generation chooses a demonstrator at random, and with a certain probability is going to copy from them, but only if their variant is A, and this is where the bias comes in. So only these 2 demonstrators have a chance of being copied from. You'll only copy from them with a certain probability, and if you do so, that could lead to you getting rid of variant B and changing it to variant A to switch. So this is the content bias. At step 2, variant A is now somehow favored and B is not. And we'll call this probability of copying variant A at step 2, S for the strength of the bias. Now, that seems like a fairly involved setup, but can anyone see anything vaguely that would be real worldish about this idea that first you copy directly from one demonstrator, but then subsequently you choose a demonstrator to perhaps copy from? To me, it's not perhaps entirely like learning a first language if you believe that first you learn from your parents and later in life you go and associate with other people and perhaps you change your behavior with them. So again, it's a very idealized model, but the idealizations are not obviously ridiculous, and it's worth looking at what happens. So what is going to happen when we let this run over multiple generations?
So what I don't understand about this intuition is why. So I can think of a real world example easily where you're likely to copy from some demonstrators because of the social properties of these demonstrators. Not because of the hypothesis, not because of what they are exposing you to, but because of other nice characteristics that they have.
Great. So, and what you just described is a 5th model, which is not going to appear here, which is transmission with indirect bias, where it is not the variant that has the bias towards them, but instead the demonstrator that has the bias towards them. And it is true that that is probably more obviously relevant for linguistics. In cultural evolution, where this came from, the idea that a variant might have a bias could be things like you're building tools and one of the variants is better than the other.
Yes,
and then, and so a real question that we have to ask ourselves when we apply this to linguistics is, oh yeah, so do you really think variants are like this, that some are better than others? And I'm not going to say anything about whether I think that that's true or not at this point.
I'm wondering whether the new syntax of a German while could be an example. Usually, while introduces causal clauses, and as in any subordinate in German, the verb should be at the end, subordinate clause. But it has changed in recent years. And now it is also used with the word order that is used for main clauses.
Yeah.
Because main clauses are a nice model to go by, and also because there is another element which is then that logically makes more or less the same thing as while, and then has always used the main clause.
Okay, great. So this is a nice one. So we've got in German a while clause. Traditionally, you put the verb at the end. Main clauses, you put the verb in verb second. What's happened recently in German is that people are using weil with verb in verb second position. So it's, you not only can say weil ich sehe, but weil ich sehe dich, or because I see you. And there might be a reason why that new variant is biased towards, because it matches the template from the main clause, and it also matches a template from a semantically similar clause that starts with den. Right, so there you go, good. So we've got a hypothesis, well, a scenario where it's not ridiculous to think that maybe one variant does have an advantage over another in linguistics. With that said, let me move along and see what happens if we assume that this is the model we're going to use and run it. So first, population of 10,000 individuals, or 1,000 individuals. And here I'm going to start off with the prevalence of A at just 5%, but remember there's a bias towards A. And you can guess what kind of diagram I'm about to show you. Put down your money, but I'm not going to pay you anything. Here it is, an S-curve. We got it. So this is with S set at 0.1. So if you've chosen a demonstrator that has A and you have B, there's a 10% chance that you switch. And if we set S at 0.2, we've got an even steeper S-curve. So this is nice. We've got a model of transmission with content bias. It comes from the field of cultural evolution. Now, we've just had a great discussion about how it might fit with language if we're careful. Really interestingly, this model is exactly equivalent to another foundational model, which comes from epidemiology. So let's see why. In this model, we have the same parts of the model with the same relationships in the model, but we're going to give those parts and relationships a slightly different interpretation. But all of the relationships in the parts are the same. So trait A now means, because we're in epidemiology land, you're infected. And trait B means you're not infected yet, but you're susceptible to being infected. And so now we're going to model individuals who can be susceptible or infected, known as the SI contagion model, susceptible, infected. Now, instead of thinking of step number one involving 2 generations, think of it as involving the same individuals from time t and time t plus 1. To begin with, individuals just continue in the same state that they were. Effectively, at time t plus 1, you are a copy of yourself and your status at time t. Then, step 2, everyone, unfortunately, interacts with other people. And at this point, if you interact with someone who's infectious, then with some probability, you become infected. But it's all of the same parts and the same relations. So since the SI model is exactly the same, has exactly the same form and structure, its dynamics are also exactly the same. So we also get S-curves in epidemiology. The only difference here is that the horizontal axis is no longer generations, instead it's time intervals, such that in each time interval, a person will interact with one other member of the community. So previously, when I was showing you the S-curve, you might think of that as how something like, say that's these while clauses are going to change over many generations, right? This may be something like, what's the latest word to say that something's cool, which is changing over, time steps in your own individual life. And again, we've seen reasons why we might expect an S curve. Again, highly idealized, lots of stuff that's not in the model, but we're turning up some really quite interesting results here and stuff that we should sort of keep in our little toolkit of baseline models against which we can compare other stuff. 4, let me very briefly mention transmission in social networks. So until now, our models have allowed individuals to find their demonstrators at random anywhere in the community. If there were 1,000 people, you could pick from all 1,000. But of course, real communities have structure. So an important set of models of spread, both in cultural evolution and in epidemiology, obviously examines spread within social networks. So for instance, if this is the dots of people and the lines are who they associate with, this is a highly clustered network. Each individual has contact only with 2 neighbors to each side. And those neighbors are also probably in contact with some of the same people. So it's very tightly clustered. What happens now if we take not this little circle, which only has 12 people, but 1,000 people, but in a similarly connected circle. And we then run a scenario of biased transmission or contagion like we did before. What do you think it's going to look like? And whatever you guess, you might be surprised to see that it's that. It's basically a straight line up to the point that everyone's infected or everyone's using variant A and then it stops. Why is that? Because basically the things are spreading out kind of along a straight line. They're so constrained that's what happens. What is really fascinating though is let's take a very slightly different network. This is the same network except I've unlinked something here and joined there. And there's one other, and a link here I've unlinked and joined it there. So there's only 2 links different. This is what's known as a small world network. It looks very similar, but it has really different properties. If we run our model through it, we get something that looks like this. That's 5 different runs, and each of them is an S curve, approximately. And also, notice how much quicker it is. So if you were going to have a pandemic, you would want to live in this town, not that one, but we all live in this one. Is the thing. And also that's really interesting for what it's going to mean for linguistic change. Again, though, this is a super basic way to start, but as you can see, there are really interesting questions and interesting ramifications of looking at things in social networks. So
what's the crucial difference? So the crucial difference is that someone is more influential, but there's
no, everyone has got just, oh yeah, this is a bad example. No, everyone actually has 4 links. No one's more influential. It's just some links are just distant. Some links leap across to the other side of the community. It's not that anyone's more influential here. Yeah, so thanks for asking that. Of course, we could consider social networks where someone does have more contacts, and obviously people do that. Yeah. Great. So I won't go further there because I need to move on, but there are obviously many directions in which these models of innovation and spread could be taken. Here I've just looked at the absolute basics. We've seen unbiased transmission, which just produces a flat dynamic with some noise around the status quo. Transmission with mutation produces R-shaped curves. Transmission with content bias produces S-shaped curves. And social networks were, well, complicated. Of course, all of this plays quite an interesting role for language change. In language change, empirically, we know that there are lots of S-shaped curves out there in the real world. Yet, to go back to a question that was kind of raised, is that because we believe that the world is full of content bias? Is that what we should be concluding from that? And so that's a question that the linguistic modeling inference literature has been very, very interested in, and it reflects this kind of conundrum. So in 2009, Baxter and colleagues argued that in order to model the emergence of New Zealand English, which Trudgill had studied, you need to assume content bias, or at least you wouldn't get to it with unbiased transmission alone. It wasn't sufficient. You would need far too many generations to get the result. that we see. And that's based on a really quite sophisticated and elegant model. Others, though, have tried to derive S-shaped curves without content bias. So just to mention a couple, Stadler and colleagues examined the consequences of having individuals who pay attention not just to which variant you use when I'm interacting with you, but whether that's changed. So what's the speed at which things are changing? And the idea is that if you pay attention to momentum, that can kick off an S-shaped curve. Pierre Humbert and colleagues explore what happens when we have people in a social network and we have individuals who are different to one another. Some of them are particularly inclined to adopt innovations and others are not. Moreover, those people tend to be clustered in the network, and in that case, we can get some interesting dynamics that you wouldn't get without those assumptions. And then Calvin in 2017 looks at the effects of having social networks that are constantly dynamically changing as people are dying and being born, and looks at whether you can get S-curves there even without content bias. So all of these are very interesting papers. They're just a tiny fraction of what's going on. But just to finish off, this is what we've looked at in terms of these foundational models of spread. If you found the little models that I was showing you interesting, I highly recommend. This is just an astoundingly good collection of tutorials. They are classic cultural evolution models. There's 18 of them, all of them with the R code. And Alex Westmoody walks you through the theory, the key papers, and teaches you R along the way, and has all of the R code there available so you can run it yourself and change the numbers and try it out. Really brilliant. And they just appeared a few months ago. There is a accompanying textbook as well. But if you're interested in this kind of stuff, I just can't recommend it enough. It's really, really brilliant. Okay. Last topic for today. Let me now turn to a Bayesian admixture model of language contact. And that already looks like, you know, something that is at the top of a paper in PLOS or Nature or whatever. Or perhaps increasingly, your favorite linguistics journal, right? Which is why we're all doing this. So the model I'm going to talk about here is a model called structure. Structure is getting pretty old. It dates back to 2000, and it is very, very widely used in biology. It's got tens of thousands of citations. It's a good, useful model. And it's used to study cases where there are processes of admixture amongst populations which lead to individuals of mixed heritage. That is to say, there's a mixture of traits that we find in an individual that are characteristic of more than one source population. In biology, this can arise through the interbreeding of two populations or more populations. In linguistics, we might think of this as being somehow related to language contact. And so what I'm going to do now is introduce structure, the model. Then I'm going to mention some applications of the model in linguistics. And then what I want to focus on here is something that I haven't done as much so far, is one of the points that I made last week, is the really importance and sometimes the real difficulty of interpreting models, particularly at this moment in linguistics, where we tend to be at the stage where we're borrowing models from others and trying to fit it against linguistics. And sometimes it works, sometimes, well, I'll see what you do. So the structure model is a bit intricate. So let me start by describing what it does, and then I'll talk a little bit about how it does it. So structure begins with a set of languages. Each of those languages is described in terms of a set of characteristics. So think of this like a typological survey, which has been done for a bunch of languages. Or if we want to introduce a little bit of biological jargon here, they get called characters. Normally, a character will be a question on a survey in linguistics. So in Bayesian terms, this is the evidence that we're going to give to the model. The model then evaluates hypotheses about a small number of sources from which these characters have been drawn, such that each language draws its characters from multiple sources and mixes them together. So for instance, structure, this is going to be interesting. Apologies to the people in the room. Those who are online, you can see the full color. Here in the room, it's just shades of bleh. Anyway, structure might infer that most likely language A has drawn 75% of its characters from source X and 25% of its characters from source Y, and we can draw a colorful little bar there to represent those proportions. And then if we plot all of the languages in our sample, we may end up something like this. And you might have seen one of these diagrams in papers that you've read. And this is nice. What it does is it gives us a picture of how each language, which is the vertical bar, is drawn from different sources. And it also gives us an idea of how the sources have contributed to different patches of languages. So it's really quite nice. And the plot here that I'm showing you is from a linguistic study of 121 languages from Australia and New Guinea and the islands around there. One key effect of the model is that it produces what is known as a soft clustering of the languages. That is, it puts them into color-coded groups, but it doesn't say that every language is only in this group and not in all of the rest. It's this one mainly and partly in this. So that's called a soft clustering. That's one of the effects that it does. Now let me talk about something quite important. Structure makes a significant distinction in the representation that it has of languages per se versus the sources from which they're drawn. So these two things are going to be represented really actually quite differently. So languages are represented by characters with actual values. So character number 1, are there uvular phonemes, and the value will be yes or no. Is the dominant order SOV? The answer might be yes or no. In contrast, the sources are conceived of as populations which have some internal variation within them. So one of the idealizations of structure is that those populations, it doesn't keep track of everyone that's in that population. Rather, it just keeps track of some overall properties of the population. And consequently, the characters for a population are represented by frequencies of values. For example, in population X, are their uvular phonemes is 14% yes and 86% no. Or is the dominant word order SOV 60% yes and 39% no. So this is really different, the representation. Languages, which we've got our actual data set for, have specific values, but the populations just have percentages which represents the variation within them. So when structure models language contact, it's not representing a set of languages interacting one-to-one like we might typically think about it. Rather, it's representing a set of ancestral populations of languages that have contributed different amounts to the modern languages. Moreover, this is the only process that occurs in the model. This is, again, idealizations that leave out parts of the real world. The characters are drawn from multiple sources. That's it. There's no language internal change of characters per se. There's no sound change. There's no grammatical change itself. There is just the mixing of exactly the properties that we can find in those source populations to build yourself a language in your data set. Now, at the end of this section, I'm going to come back and ask the question about how appropriate that might be as a model of language contact. For the moment, though, let's say, yep, we're happy with that, and have a look at the model and how it operates. So in Bayesian terms, what's going to go on is this. We have bottom-up information that's from the characters of the languages that we've got. That's our data that we've collected in our typological survey. The model is then going to evaluate the probabilities of hypotheses about the sources. That is, the nature of the sources themselves, what are the frequencies of the character values that they have, and what are the partial contributions of those sources. So information, if you're wondering where does that come from, it comes in the form of certain expectations about these probabilities, about how internally diverse the source populations are, whether the languages typically draw from few populations or from many. We control that in a top-down way. It's rather technical. I thought I'd mention it since I made such a big deal about top-down information before. In this model, the hypothesis space is really large. There are many, many conceivable populations with different frequencies that contribute in different ways to your languages. And accordingly, it's searched using one of the techniques that I made mentioned in the first hour, which is Markov chain Monte Carlo. And I will not skip the next slide because I think we're going to be able to get through this. Right, let's go in a little bit deeper here. At this point, if maths makes you feel uncomfortable, check your email for about 5 minutes. But I am trying to keep this accessible, right? So it's only if you don't like the idea. So the principle is basically what I've written here. We propose a hypothesis, evaluate its probabilities, adjust the hypothesis, and repeat. So adjustments are going to be made, kept or rejected, depending on whether they're improving the probability of the proposal. We want to keep getting proposals that are more and more probable until we've got, really, really high probability proposal. How is the evaluation done? So using Bayes' rule. That's why it's a Bayesian model. In fact, as I mentioned last hour, because the evidence here is fixed, this is not changing. We're not changing our languages along the way or anything. We can just ignore that, which is nice. That makes it a little bit easier. The prior here is given by certain technical distributions that we use on the data, so we don't have to worry about that terribly much. All of the action is going to happen with the likelihood, this bit here. So let's take an example to see how it works. So for language A, in a data set, the character is the dominant word order, SOV, has the answer, yes. That is a piece of evidence. So what is the probability of the evidence given a hypothesis that we are entertaining? So suppose that the currently proposed hypothesis states that language A draws 75% from source X and 25% from source Y. And it states in the current proposed hypothesis that over in the frequencies in those sources, source X has an 80% frequency for that answer to that character, and source Y has a 40% frequency for that answer for that character. So this is the current hypothesis, and we want to get the probability of the evidence given that hypothesis. So this is what we do. We just apply the kind of formula we saw before, and we can get our answer. So what we're doing is multiplying those things. The overall probability of a yes value for this character, given the current hypothesis, is the probability of drawing from source X multiplied by the frequency of that answer in X, plus the probability of drawing from source Y multiplied by the frequency of that answer in source Y, and we just add it up and we do it there. Now we have the answer for one of the characters in one of the languages. We go into this for all of the characters, all of the languages, for every hypothesis that we propose, but every time we can get an answer here, and we can check that as we adjust our hypotheses that we're moving towards higher and higher probabilities. And that's basically what it does. And so you set it up and you go and make yourself a cup of tea and take yourself out to a movie, go on a holiday to Norway, come back, and it gives you the answer. Right. So structure has been applied in a number of linguistic papers now. Reesing and colleagues was the first in 2009. This study looked at 121 languages of SARPL, that's the continent that joins Australia and New Guinea, and for most of its human occupation, they were actually joined, and islands around the area, so they're looking at some really deep time stuff. That's a part of the world that has over 50 language families, so they're looking at some pretty adventurous data there. Not all of the 50 are included in their data. This is a nice one. Last week, Hubler and Greenhill published a study looking at 60 languages of the putative Altaic group, so Japonic, Koreanic, Mongolic, Tungusic, and Turkic. Norvig in 2022 look at 35 languages now within a single language family, Uralic. And and this is one I really like. Surrey and colleagues in 2016 analyzed a massive 525 local lexs of Finnish using 300 characters to study variation in Finnish. And this one is cool, but not directly relevant. Bowen in 22 is a study of documents of Tasmanian languages where the documents had mixed together the actual language varieties. So it's not language contact, it's documentation contact. And she was trying to figure out how many underlying languages were there in this sort of mixture of documents. Really, really nice, but a little bit different from what we're mainly interested in. So here's a plot from the Finnish study. It's giving you a close-up of a little area in Finland, South Ostrobothnia. Now, what we've got is some color showing the different sources or clusters. Along the left edge is the coast, and there was no data there. But going down the middle here, the reason they've left it white is because these are extremely admixed areas where it just doesn't seem to belong to any one of those clusters that they've got. So this is one, and if there were color here, you can see that it's got all four. So it's very, very mixed. And so that corresponds to something that may not surprise you. Here is the results from Sahul. Now they've got 121 languages. This is an area with 50 language families. Interestingly, about a third of the data set all belongs to Austronesian. Trans-New Guinea is possibly a very, very deep language family in New Guinea. Non-Trans-New Guinea means the other 24 language families. Similarly, Pama-Nyungan is a big language family in Australia. Non-Pama-Nyungan means the other 24 of them. And I will keep this thing up on the next slide. You'll notice that the clusters sometimes match the families and sometimes, interestingly, don't quite match the families. Yeah, that's what they said in the paper. And therefore, we can find out wonderful things about really deep time history. It was one of those early sort of very boisterous papers that said that they could do wonderful things, and then you look at the details, it was much more hedged when we get into it. So I am glad that I've arrived here at this point. What I want to do is, rather than me finishing up by just giving you a summary of what I just said, is to try and go to some discussion. Because there's interesting stuff in here. Hi, people online. We're at this.
Just the sound one. Oh,
I did,
yeah.
yeah. So we're at this discussion slide. Questions are, how well does structure represent its target system? What even is the target system if we're talking about language contact and deep time? And how do we interpret these clusters, given that the description I gave you was populations of languages? I'm not sure what that would be in linguistics, but maybe someone in the room can see some way of thinking about it. So I don't know if anyone wants to dive in and just comment on any single piece of this that might have struck you as you're seeing it, or you might think about it. If you know about language contacts, does this seem a good way to do it? Do the results seem plausible? This is sounding like a discussion in my own mind. You look like you have a.
Yeah, what's my biggest question mark, I think, is what are we trying to do? Because clusters mean things depending on what we're doing. Right?
Yeah.
So maybe for your families, you can tell us a little bit more about what you're trying to do with having this.
Yeah, what I'm trying to do is showing this to us, or what I'm using it.
Sorry, not your best the word. Yeah.
Yeah, right. That's a really good question. And if you read the papers, I think what they're trying to do is use structure. Summary of what's similar and what's not. But then it's like, well, why did you bother doing that? We could have done that in other ways. And that's where the discussion in the papers kind of, I would like to have seen more of that. But perhaps is the question you're asking me, what did the papers say? And my recollection is not much at that point.
So, yeah, I have a naive question. So how exactly, I mean, of course, we try to model language change, but you talked about like going back for such a long time. And how did the system exactly do that? Because that wasn't clear to me at all, how this like time dimension came in.
Yeah, so this is a really interesting thing. This is for linguists, quite a mind-blowing idealization to have in your model. This is a model of language contact, of things that happen over time, but the model doesn't actually have any time in it at all.
Okay.
It's just a variation here, another one here, another one here, and I just draw from them and assemble language A, draw from them and assemble language B. There's no actual time steps.
Okay, so then that's like a hypothesis or so on the basis of like the, because I understood you correctly that you talked about like going back thousands of years.
Yeah.
Yeah. And I still don't get it.
Yeah, so first of all, let's note that it's not entirely unreasonable, right? So let's say we've got our languages that we're going to end up with, and we've got these, let's say these are whatever they are, these populations, many thousands of years ago. And what first happened was there was this one kind of descended down to this, and these two mixed together and descended to that. And also that one descended to that.
Okay.
These two mixed together and descended to this and that. And then they all went off in different ways to the languages here. Actually, mathematically, you still end up, if that's the case, with a certain amount from each of these that ends up in each of these. So it's perfectly reasonable to do the idealization that we just want to talk about what happened in between, because we're just saying, ultimately, where did these characters come from up here?
Right.
What starts to stretch it, I think, a bit is that what ends up in these languages is the exact trait value from up here. There's no change. That if it's phoneme P here, it's phoneme P up here. If it's SOV order here, however many bazillion years ago this was, it was SOV, and it was that the whole way through. It never changed. It was just shuffled and mixed with other languages, and that's obviously not what happens in the target system. The question is, how good is the model if that's been idealized away? There are, I think, a few more. Yes.
Thank you.
Yeah, somehow the color thing, as you just said, strikes me as being achronistic. So it doesn't show the time depth that is there. I mean, a decently done 19th century study of language or dialect would probably, even the availability of data, obviously, has said much the same thing. So, for instance, a language or dialect X or Y has a lot in common with a neighboring language X or Y, but in other respects we find
Absolutely.
traits,
Yes.
language there.
And that's one of the reasons I really like the Finnish studies, because there is something, there's a whole lot of scholarship already that they related to, and they show that, yes, this is reproducing the same kind of thing. One of the nice things about using structure is it's computational, so we know that it didn't overlook some data, or it wasn't biased towards a certain answer that it wanted to get because Professor so-and-so said it wasn't that. So that's nice there. And that's one of the reasons why I've kind of obviously been happy about the Finnish study. I find it easier to interpret, whereas something like this, we don't have something really to compare it to. But your comment that it's achronistic, I think is an absolutely correct characterization of the model, as we were just discussing. And then that's actually really nice, because that helps formulate the question a little bit more carefully. How good can an achronistic model be of a target system where there's a lot of chronicity?
Given that we know things about language change in general in those languages for which we have a certain kind of.
One thing I'll just mention is, let's say we were doing this with one language family, and the language family looked like this, and proto whatever was SOV, and over here it changed to SVO. Then these two are going to be SVO, and these are going to be SOV, and cluster is going to put these, sorry, structure is going to put them in one cluster, and these two in another one. That's what it will do. And you can ask the question, well, is that useful for us to know? If we're trying to model language contact, then perhaps we don't necessarily want things like dominant word order. If we think that they're mainly inherited, maybe we want a whole lot of features that we think are easily spread by contact, or so forth. Now, I should actually just go back and say, to be fair to the papers that have done all this, when I say that they haven't answered these questions, I don't mean that they haven't had a tough time about it and they haven't apologized for not answering the questions. Many of them do, but I find it really interesting, and I thank you for the discussion here. It seems that the structure was first used in 2009 and then wasn't much, but there seems to be a flurry. It seems to be getting going again. And there are other similar admixture models that are out there that I think we'll see more and more in historical linguistics. And that's one of the reasons I wanted to introduce it, even though there's all of this uncertainty around it. We are the community that has to respond to that kind of research, and the more of us who can have some sort of idea of the questions we would like to see addressed in a paper, the more we can push along the research. And so that the people who are developing models and using them can get tested a little bit more by us who are not using it, or if we want to start using it, we can do it with sort of a bit more knowledge about what's going on. As much as, you know, we may be 10% in the light and 90% in the dark, you know, that's better than 100% in the dark. That's all of the time for this week. So thank you very much. Next week, I will start with phylogenetic models, and then we'll finally get to morphology.